Hello, this is Robert Murphy again from the University of Colorado in a series of lectures and videos on lipidomic studies using mass spectrometry. This particular video will cover some of the aspects of quantitative analysis of lipids, an extremely important part of lipidomic studies and one that has a lot of potential diversity in how one implements this. So this video is going to deal with the quantitative aspects of mass spectrometry lipidomic studies. And we'll talk about some of the features which make it a unique way to measure lipid substances in biological systems. So this is the sort of middle part of a lipidomics strategy, and it has a couple different forms of how we carry out lipidomic studies. So let me start with perhaps the easiest one to think about, and this is when we generate a standard curve of the lipid of interest and we use an internal standard. And so typically what we're trying to do is to generate a curve like this. So the secret in all of our quantitative studies of mass spectrometry is that we are going to deal with the intricacies of what is the intensity of the ion which you are measuring, or the ion transition if it's a tandem mass spectrum. And this is my attempt to explain the relationship between the intensity of the observed ion that has a certain mass to charge ratio, and it's going to be indeed a function of the lipid concentration, that's what you want, but also a function of the ionization cross-section of the molecule that you're studying, the ion stability of the ion or ion transition you're looking at, as well as some unique features of the sample and what may also be present in the sample to change the intensity of the ion you're measuring, as well as instrument factors such as the performance of the instrument, or even the type of instrument you have, a time-of-flight machine, an Orbitrap, a tandem quadrupole, and whether or not you have focused it correctly and calibrated it correctly, and it is clean and is in sort of performance level. And then lastly, the performance of the electron multiplier in that machine and its response to a beam of ions hitting it. So all of these have a tremendous effect on the intensity of the ion, and they modify the relationship between the concentration of the lipid and the intensity of that ion. So in other words, what we want it to be is related to the concentration of the lipid, but we have ion chemistry playing a role in modifying that relationship. We have interfering compounds, which could be other lipids, which alter that, and also the operating parameters of the mass spectrometer, and in particular the electron multiplier. So all of these make it so difficult to make a valid relationship between the lipid and the intensity of the ion which you observe, that for many years people thought it was impossible to use mass spectrometers as quantitative tools. But that changed when a very simple solution was suggested for this problem. And that's what I call the secret of quantitation. We reduce the quantitative measure to a ratio measurement. Rather than measuring absolute ion abundance, we're measuring its relative. And it's relative to an internal standard. So that's the entire secret of quantitative mass spectrometry. And so what happens is that if you use an internal standard, this equation, which has all of the interfering lipids and the type of mass spectrometers, confounding thing, is reduced to the concentration of the lipid and then the unique ion chemistry. And you can even reduce this further if you use an isotope labeled internal standard. Now, for this relationship to understand what this relationship really is, what we typically do, rather than having absolute numbers we put in here, we do an experiment where we take reference material, in other words, the molecule you're trying to measure, for each of the molecular species that you are trying to measure and generate a regression line for the relationship between the ratio of this mass of the ion of interest and its internal standard response to the quantity of lipids. So we actually empirically determine this equation here, and it's a linear relationship typically, so we do a linear regression. And here's an example of one of the results of doing this experiment. So this is not done with your lipids of interest, but with reference material. So in this assay, this is now measuring cholesterol esters, and we're going to be using tandem mass spectrometry. We're going to look at the ammoniated molecular ion of cholesterol esters, and when you collisionally activate them, they form the ion 369. Now, what you see on this graph here, you have picomoles of reference standard, and then you have the signal, the ratio of the target molecule to the signal for the internal standard. So this is a series. There's about 10 different cholesterol esters starting from 14.0 and going down to 22.6 cholesterol esters. And what you see, there's actually a relationship between the carbon length and the double bonds. The ratio changes because of the ion chemistry of the fatty acyl group. And this is one of the natures. In fact, one of the bigger effects is the number of double bonds. As you see the number of double bonds increase, this slope becomes steeper. So it turns out the calibration curves have to be drawn for each molecule if we're going to use one internal standard, which is non-isotope labeled molecule, although this particular case we did use an isotope labeled internal standard, but it was one that had 18.1 instead of 22.6 or 14.0. So we empirically determine the equation of that line from this relationship of the ratio of the signal to the concentration of the sample. Then with that equation of that line, we apply the observed ratio we measure with an experimental sample, and then can actually calculate directly the quantity of material present, number of picomoles of present. Okay, now, as I had mentioned, if you use an isotope labeled internal standard, this equation becomes really simple because the ratio of the internal standard is equal to the concentration of the lipid. And of course, it depends on how much internal standard you have and what the actual slope and so on like that. But when you put this in mole terms, a linear regression really have slopes very close to unity. And if they don't, it's the internal standard is not pure or the reference standards are not pure. So that's sort of an interesting feature of what these standard curves can tell you. So let's talk about more detail about these internal standards. And here's some of my thoughts about them. Well, the first question I'd like to ask, do you think the number of isotopes in the internal standard matters? So here's a sample of a D4 standard, and it's got a little bit of D0, a little bit more D1, some D2, and then a lot more 3 deuteriums. It's got maybe about 30% of the deuterium atoms in that molecule are deuterated, and probably 94% are D4. Does that matter? Okay, we'll look at that. Does the chemical purity of the internal standard matter? In other words, if you weighed out some of the internal standard and it turns out it was a sodium salt and you didn't know that, and of course you weigh out the sodium salt along with it, does that matter? Do you really have to know the chemical purity? And then do the natural abundance of isotopes of the target molecule, do they matter? So we'll look at these independently here. So here are some theoretical standard curves, and I plot them so we can see the range of this. This is a log-log plot here, and I've used as example one of my favorite molecules, leukotriene B4 picomoles, and here is the ratio of the transition of 335 going to the product ion, in which case is 195. I didn't put that here, but anyhow, what happens if you're using a D1 LTB4 internal standard? So it turns out the plot looks like this, not a very big dynamic range. And in fact, it asymptotically becomes a nonlinear region, non-changing region at the low end, which happens to be the purity of, or the amount of D0 which is in that internal standard. In this case, it was 10%, 10% D0 in the internal standard. So let's reduce that to 0.1% D0. Here's 0.1% over here. And now we're going to use D4 instead of D1. And so now we're going to come down to these numbers here. This is the natural abundance, and this is the purity, isotopic purity of the internal standard. So now you see with this one here, this one has a much wider dynamic range, and it doesn't even asymptotically fall out until you're down to this, this very low number of the natural abundance of LTB4 at MRC 339, or the fourth C13 of LTB4. And then the top also goes quite a bit higher. So you see that the number of isotopes you have makes a big difference. You want to move out of the natural isotopes of of your lipid of interest. You want to have at least 3, if not 4, maybe more stable isotopes. And you also don't want to have very much D0. D0 really limits you to what you're going to be able to measure. Now, and that's because this ratio is not exactly the way you may think. It's not the ratio of LTB4 to the ratio of the internal standard. It's LTB4 plus the D0 content, this one, that's what's up at 335, and then this ratio down here would be, for example, the ratio of the internal standard, 339. It's the amount of internal standard plus the natural abundance of that number, which is that one down there. So they're a little bit more complicated. This is where the natural abundance numbers are. So the actual theoretical standard curves in a lot of space is shown here, log space, in which the asymptotically comes down to these lower levels where you are approaching the natural abundance of the lipid that you have at the mass you're measuring for the internal standard. And so that will asymptotically level off. And unfortunately, most of the quantitative assays in mass spectrometry are in this lower region. So this can really drive the ultimate sensitivity of your method. Now, the isotopic purity of your internal standard at M plus 0 or D0, it will asymptotically come up here to wherever that number is. Now, typically, that's not a big problem. Okay, so now let's talk about another aspect of this. Now, we've been dealing with the concept of absolute quantitation. In other words, you're going to measure picomoles of the lipid of interest. Now, a lot of targeted lipidomics really is set up to do absolute quantitation, in which case we have internal standards and reference standards. We can draw the standard curve. And I want to point out that the purity of the reference standard is really critical for the quantitation that you are measuring. It drives the accuracy but not the precision. For example, if your reference standard is only 50% pure, you're going to be incorrect in your measured abundance by 50%. So you really want to make sure you have really high quality reference standard material. And I know that Avanti pays a lot of attention to this, and this is really quite important that you have good standard material. Now, for the internal standard side, the purity is not critical, and this surprises a lot of people. They haven't really thought too much about this. But if you add, if your internal standard is 50% pure, and you add the internal standard is only 50%, it doesn't matter because you add the same amount to every sample, and then you divide that out by into the response of the reference standard. So that number cancels out. It just means that the signal is not going to be as big for your internal standard as what you might thought, but it turns out as long as it's constant, that's all that matters. It just has to be a constant denominator. So the purity of the internal standard is not that important. So we can get away with using isotopically pure molecules, isotopically not so pure molecules, those which have maybe a lot of D3 and D2, as long as we measure just the D4 as the signal. Those don't interfere at all. It just decreases the chemical purity of the molecule per se. Okay, so the accuracy, as I have indicated, is really determined by the reference standard. And so if you want to be within 10% accurate, you probably want to have better than 90% pure reference standard, but typically you want to have 1% pure accuracy. You probably have to deal with 99% pure reference standard. And the internal standards, you choose them because they have a large number of isotopes, and you get them away from the natural abundance of the molecule you are measuring, and you get very, very straight lines. As you can see, a very nice linear equation. The correlation coefficient is very high. And typically, this is what you expect for a stable isotope dilution assay using mass spectrometry. The other really important thing about quantitative analysis, and especially this absolute quantitative analysis, is that you want to determine the analytical figures of merit of your particular assay and calibration curve. So the calibration curve is only made with standards, so very often you are not you don't know what effect the matrix may have, that's the sample effect in that equation, may have on your measurement of the ratio of ions. And so to test that, you probably want to spike your biological fluid near what you've determined to be the limit of quantitation of your method, or maybe the limit of detection of your method, and make sure that you can actually detect the newly added molecule to the biological fluid. To do that effectively, you got to really establish the signal to noise that is acceptable. And finally, what's really important, you must look at the data yourself. Don't rely on the computer-generated values, which are being churned out. You need to look at the data to really assess these qualities of your analytical figures of merit. So here's some data, and this is computer generated, so you're not looking at the data itself. But here they've determined, in this case, it is estriol, and the limit of quantitation is 1 picograms, and so that's what their limit of detection is, and for estradiol, it's 3 picograms per mil coefficient of variation. So these are really important to be able to determine and state where you are working. Now, this is an example of some data from a study, fairly recent study, in which they were measuring estradiol in serum. And here you can see that we have 2 ion traces. One is for the transition 271 to 145. The other transition is 271 to 183. Now, these 2 ion products are made from estradiol in virtually the same amounts. And indeed, this experiment shows you that at the correct retention time, the abundance of these 2 ion transitions are almost identical. So that reassures you that you're really truly measuring estradiol. So we call this a qualifying MRM, to qualify that you're measuring the right thing. In contrast, a much lower level of estradiol present in this serum, closer to the noise level of the system. In fact, we see a peak, which actually is a little bit pre-eluting, but it doesn't have the right ratio of the estradiol 2 ions. In fact, the transition to 183 is not nearly as abundant. But the later eluting one, slightly different retention time, does probably have closer ratio. So you think this is probably qualifying that ion and that chromatographic peak as the correct one for estradiol. So that's a useful thing, is to make use of the ion chemistry which is available to you to really have this ability to make sure you're measuring the right thing and not be confused by another peak. So here's another example. This is a prostaglandin example. Here's the transition 351 to 271, and there's lots of peaks coming off at this retention time around 6 to 7 minutes, 5 to 6 minutes. And if you look at the D4 PGE2, you see it's a single peak, and it's sort of right in here. It's not all these other peaks. So what are these other ones which are in here? And you worry about this, and by looking at the data, the signal the computer may tell you there's this amount of blue peak in here and integrated that area, but have been totally wrong. So what are these things? Well, these things are what we call isoprostanes. They're made by free radical oxidation of lipids in biological systems, or maybe during the isolation of the of the prostaglandin E2 from lung lavage. And in fact, when we do this same experiment of this one here of looking, that's the same data, looking at the transitions in the mouse lung, and now we work it up with some antioxidant, butylated hydroxytoluene, we see those all disappear, and indeed now we have a peak which is right at the point where a deuterated standard is. So it turns out those other peaks were artifacts, and you would not have known that had you not looked at the data, and you knew how to then address it by adding antioxidants. So it's really important to look at the data with your assay, that you're measuring the right thing, it has the right retention time, and possibly if there's another transition to look at, the transitions have the correct ratio. Now, the second part of what I want to talk about is really an alternative to absolute quantitation. And I'm going to term this relative quantitation. And I want to propose to you that this is a reasonable approach to do some experiments, not all experiments. You can't there are some experiments where you can make a really significant advances if you don't go through all the trouble of doing absolute quantitation. So what is this? Well, this is reporting the ratio themselves and then comparing the ratios between samples. And so you might have an experiment you're looking at. Let's say you want to look at knockout versus a wild type cardiac tissue lipids, or you want to look at the urine of animals treated with a drug, and you want to look at the effect on certain lipids in the drug, control versus drug treated. Or you expose cells to one agonist or another. In these experiments, very often we were looking at a large number of lipid families and lipid molecular species. We're really unable to add an internal standard for each and every one of the lipids we're going to be seeing in the mass spectrometric experiment. So I'm going to raise the question, maybe only one internal standard is adequate or available. So this is sort of where the Avanti product splash internal standards come in. They're a series of deuterated internal standards, but there's only one molecular species for each of the classes. There's one PC internal standard, one PE. But in normal systems, PCs, there can be 500 different PCs. You only have one internal standard, and you can't make 500 internal standards. So this is where this relative quantitation has some value. In those cases where you have hundreds of molecular species, and those are triglycerides, sphingolipids, and phospholipids, there's really no way you can obtain internal standards for everything. So you say, I'm going to accept the errors I'm going to have by having a homolog internal standard, and I'm only going to use one. But you can still use reference standards if you want to quantitate that, but maybe just you looking at the ratio might be useful. So one thing is this is now cholesterol esters, and we're looking at the signal of internal standard. You get the ratio of that number, and then you calculate the ratios for these other molecular species, and that's the ratio we're talking about. So we're going to talk about the ratio of just the ion abundance of the transition or the single mass to the internal standard. Okay, so we're going to report the ratios between the different samples in the experimental paradigm. So this is actual data, and this is raw data from a mass spectrometer that we got in collaboration with Rosalind Coleman at University of North Carolina. And this is now phosphatidylcholine molecular species in the mitochondria of mouse heart. Now, first thing when you look at this, you see all the different species which are present here. And then you look at blue versus red, and the blue is a control animal, and the red is a knockout animal. It's acyl-CoA ligase 1 knockout. And you see that there is a big change between red and blue. Well, we are not going to be able to get internal standards for all these, but I would maintain measuring the ratios of these to an internal standard, which is not on the scale, it's off here at lower mass, is a valid measure of what's happening in this experiment. And we can actually take these ratios and we measure this 3 times so we see what the biological variation is in this experiment. And you can see they're actually pretty tight errors in here in what these peak here. And we know from the mass we measured that is a 40 with 6 phosphatidylcholine, and this one here is a 38 with 6 phosphatidylcholine. Those are very big, and yet the less unsaturated, the opposite is true. They turned out to be more abundant in the knockout animals. So you can make some judgments, and all we're doing here is measuring the ratio. And this is valid for each species, comparing it to the other. In other words, this blue one to that red one. But it's not valid for comparing that blue one to this blue one, because we have not factored in the ion chemistry with this. But those are the same molecules, so they have the same ion chemistry. So the ratios of internal standards can be a very valuable way to now provide some insight into what's going on biochemically. Now, this is a really big slide but I want to show you data that we sort of get by using this approach. So this is now a biochemical study, and these are phosphatidylcholine species across the top here. And then these are different samples across here, and this is now PE samples, and these are PI molecular species. And the table was quite large, but you can see we measured this 6 different times with different types of variants in there, so the D1s are all the same, and then D3s are all the same here. So this data can go directly into commercial software like Metabolomics Workbench, and you can get valid information about what is happening between D1 and D3 in terms of these molecular species by just using the straightforward ratio rather than measuring absolute quantitation. So in conclusion, absolute quantitation is one of the real important features of lipidomic studies. There's a lot of absolute quantitation which is carried out. It has very high precision and accuracy, but the accuracy is driven by the purity of the reference standard. To get the highest precision and accuracy, you probably do stable isotope dilution, because it corrects for all of the variability in that equation relating abundance to the signal you're measuring. I wanted to point out to you, once again, remind you that you want to really establish and report your analytical figures of merit of your assay so people know what these numbers really are. Relative quantitation is different from absolute quantitation in that we don't get absolute number of moles of the lipid present, but we are, within comparing the same lipid species, we're able to see subtle changes that occur between the molecules, and this gives you very useful information that one can apply various statistical methods, informatics method, to reveal to you some changes which are happening in biochemistry. This is a lot easier to do. This takes a lot more work to do absolute quantitation, but relative quantitation is relatively easy to do, straightforward to do, and and if it drives you towards solving the biological problem, then this might be another alternative for you to think about.